Writing a 10-page prompt to feed an AI every business rule and coding standard at once often leads to a sudden drop in output quality. As the volume of instructions grows, the model begins to overlook specific constraints, essentially losing the thread of the original task. This happens because a traditional prompt is ephemeral and stateless. It exists only within the current chat. The moment the window is closed, every nuanced instruction and custom logic block is erased. Moving towards autonomous intelligence requires a different approach, transitioning from these unstructured, temporary conversations to verifiable, persistent instructions known as AI skills. An AI skill is a modular workflow. Instead of loose suggestions, it contains rigid instructions, clearly defined constraints, and hard-coded success criteria that the AI can execute on demand. Think of the AI as a world-class chef. A traditional prompt is a customer asking for something cheesy. An AI skill is a documented, step-by-step recipe for a margarita pizza. The chef pulls that specific recipe from the book to guarantee the exact same result every time. This enables skill injection. Instead of trying to make the AI remember every rule at once, the system dynamically loads the required recipe into the reasoning loop only when the specific task is detected. To build capable agents, engineers are moving away from single-session prompting. Building modular injection systems changes how AI logic is stored and executed, making it possible to manage complex, multi-step operations without losing reliability. Every large language model operates within the strict boundaries of a context window. This acts as the model's short-term memory, limiting the total amount of information it can process at any given moment. When you attempt to load an entire organization's standard operating procedures into that window, the noise increases. The model's attention fragmenting leads to hallucinations and missed details. The architectural solution is dynamic loading, managed through a multi-agent routing pipeline. In this pipeline, the user's request does not go straight to the agent performing the work. It first hits a supervisor AI, which functions as the system's routing logic. The supervisor performs intent classification. If a user asks to audit an Excel file for budget errors, the supervisor identifies that intent and maps it to the specific financial audit procedure stored in the skill library. The supervisor then extracts those specific instructions and injects them into the prompt of a localized worker agent. This worker agent now has exactly what it needs to complete the task. It isn't distracted by unrelated coding standards or HR policies because only the relevant logic was injected. This routing architecture allows an enterprise to scale its AI capabilities across a vast range of specialized workflows. By decoupling the instructions from the model's main prompt, you can maintain a massive library of skills without hitting the performance ceiling of a single session. A common assumption in the industry is that fine-tuning models on proprietary company data is the only way to achieve reliable enterprise automation. However, fine-tuning involves significant trade-offs. As this matrix shows, altering a model's underlying weights requires high GPU computing costs and training cycles that can take days or weeks to complete. Fine-tuned models also face model drift. Over time, the adjusted neural weights can produce shifting outputs, making them difficult to use for workflows that require 100% adherence to rigid business rules. Skill injection, by contrast, uses standard token rates. Because the instructions are text-based, they are predictable, easily auditable, and much cheaper to execute at scale. Updating a skill is as simple as editing a text file in your repository. The change is instant and propagates to every agent in the organization without a single minute of retraining. If you're looking for more technical breakdowns on how to build these autonomous systems, subscribe to the channel for our weekly engineering deep dives. Modifying an AI's underlying neural weights is often the wrong tool for deterministic business logic. Dynamic text injection provides a more predictable and cost-effective method for controlling model behavior. This modular approach introduces a specific paradox. The same mechanism that allows us to inject useful logic also allows a malicious actor to inject harmful instructions. Most people are familiar with direct prompt injection, where a user tries to trick the AI into revealing secrets or ignoring its safety rules. But for autonomous systems, the primary threat is indirect prompt injection. This is a stealth attack where the AI is manipulated by the data it is processing. Imagine a worker agent is assigned to summarize a PDF from an external vendor. The user trusts the agent to simply read and report on the document's contents. A malicious actor can hide instructions in that document using invisible text or metadata. To the human eye, it's a normal invoice. To the AI, it's a new set of commands. As the agent reads the file, the hidden string is injected into the active context. These rogue instructions can override the supervisor's original logic, effectively hijacking the worker agent to perform unauthorized actions. The agent might then exfiltrate data or provide a biased recommendation. Because the logic was rewritten mid-session, the user receives the compromised output without any indication that a hijack occurred. When agents process untrusted external data, a single file can rewrite their operational logic. Without proper security, these injection pipelines become a significant liability. To deploy these systems safely, developers must move toward dual-layered architectures that combine modular capabilities with rigid defensive sandboxing. The first layer of defense is delimiter hardening. Markers like begin data and end data isolate external information, preventing the AI from confusing data with commands. The second layer is sandboxing. When processing untrusted files, the agent enters a read-only mode, severing internal access until safe. Finally, all high-stakes actions require human-in-the-loop constraints. An autonomous agent should never be allowed to trigger a state-changing action, like making a payment or updating a database, without a manual approval gate. When these security layers are in place, the framework becomes a practical tool for complex roles. For a technical project manager, this looks like the sprint velocity skill. Instead of asking a general AI to summarize Jira tickets, the TPM injects a skill that knows the team's historical capacity. The AI then identifies specific tasks likely to spill over based on the team's unique track record. For developers, the same logic applies to a security audit skill within the IDE. By injecting internal security checklists directly into tools like Cursor, the AI flags insecure code based on the company's specific standards, rather than just general internet knowledge. Reliable autonomy today is built on modularity. By discarding the mega prompt and building expansive skill libraries protected by architectural armor, organizations can finally deploy AI that is both highly specialized and secure.